Let's talk about polynomial approximations in the context of self-driving cars. They have to have some way of expressing what they think is going to happen in the next few seconds or milliseconds perhaps. So they need to have equations kind of built in to their motion computation systems. So let's say that we're 3 meters past the most recent stop sign that we were at, and our velocity is currently 0.7 meters per second. And we're going to call right now time 0 rather than time 0 being when we were at the stop sign. Could try it either way, but let's just make now time 0. So can you write a function that says what the position will be as a function of time going forward into the future? So take a sec to write that. You probably said something like 3 plus 0.7 times t. So if t was 0, our position is 3. If t is 1 second into the future, we've moved another 0.7 meters farther away from the stop sign. I'm going to call this p sub 1 of t, which meshes with our book's notation. Wouldn't be a bad idea to graph this, right? So we could say here's t when it's at time 0, we're here at 3 meters, and we're increasing at a slope of 0.7 meters per second. All right, this might be reminding you of something you might have seen in Calc 1, the tangent line formula. Which our book writes L of x equals f of c plus f prime of c times x minus c. Our formula here is a little bit simpler, but it does have an initial value, our position at time c, whatever c is, for us it's 0, and then some kind of rate of change, like 0.7 meters per second, times some kind of elapsed time. For us, t is the elapsed time since time 0. So that's a good kind of analogy to make between those two. Now it's my understanding that cars don't always travel at a constant velocity. There's some kind of acceleration involved sometimes. So let's talk about that. So let's also suppose we're accelerating at 1.8 meters per second squared. That's kind of a reasonable acceleration for leaving from a stop sign. If it was up around 9 or 10, that would be really hard acceleration. Your passengers would not be happy with that. So what can we do to our expression here to incorporate acceleration? Well, there's two ways we can think of it. We can think of it as acceleration tends to produce quadratic change in position. So what kind of term can we introduce to our formula here to model quadratic change? Well, put it in t squared, right? So you could say p2 of t. So I said 1 here because the largest power we had was t to the 1, but now we're going to have a squared term, so I'll call it p2 to the 3 plus 0.7t plus 1.8t squared. And I'm just kind of filling that in based on intuition, like our position in meters just appeared without a t. Our velocity in meters per second occurred with multiplied by t, so it would be meters per second times second, so we get meters. So if I've got meters per second squared, I think I should multiply that by second squared. But I'm not saying this is right yet. I need to think about it some more. So this is my guess. Let's say it's a guess. So what should we do? We should check it and make sure that the acceleration is 1.8. So let's check it. P2 prime, the 3 would become a 0. The 0.7t would become 0.7. 1.8t squared would become 1.8 times 2t. And that would be, so this is the position, this would be the velocity. Would that still be 0.7 at time 0? Yeah, if you plug in t equals 0 here, you'll still get a 0.7, so that's good. Let's do p2 double prime. This would still be 0. This would be 0 now. This would be 1.8 times 2. But we wanted it to be 1.8, not 1.8 times 2. So we need to kind of go back and fix up our guess, right? So how can we prevent the 2 that comes down from the numerator, or from the power, from getting applied to this 1.8? Well, so same thing there, but we could put 1.8 times 1/2 t squared, and then when we do take the derivative, that 2 comes down, gets canceled by the 1/2, and ultimately we'll get the 1/2 that we want. So this up here was a tangent line approximation. You could call this maybe a tangent parabola approximation. All right, and then we've already dealt with velocity and acceleration, so you might wonder what's next, and that'll be in the next video.